Welcome back to Unit 5. We're going to talk about the fundamental theorem of calculus here. By the end of this lecture, you should understand that integrals can be used to define a function, and you should be able to give me a big picture sense for what the fundamental theorem of calculus says, and you should be able to use the fundamental theorem of calculus to evaluate certain derivatives. We'll start with some big picture discussion of the ideas behind this theorem, and then we'll end with the concrete skills. I think that you'll find if you have a grasp of the ideas, the skills themselves are fairly easy. So the first part of the fundamental theorem of calculus is actually something that you already know. Take a look at the picture on screen. See if you can figure out what information these two graphs are telling us and how they're related. Right, so you can probably see that we're talking about an airplane, and it's flying at a constant speed of 15 miles per minute. And you can see that because the velocity graph is a constant function, and because the slope of the position graph is also a constant 15. That's the slope. And as this plane flies, obviously its distance from where it started is changing. So the second graph is measuring its distance, and the first graph is just keeping track of how fast it's going. And then there's this interesting relationship, which is if we look at the area underneath the velocity graph and we try to calculate what that area would be, we can write it as an integral, obviously, but if we really just want to know what the area is, we would multiply the 10-minute time interval from 10 to 20 times the height of the rectangle, which is 15 miles per minute. That's the value of the function. And when we multiply those two numbers, we get a numerical answer of 150, and the units are just miles because the minutes cancel out. Why is this surprising? Well, because that means that somehow this velocity graph, which is just telling me about speed, actually contains some information about distance underneath its curve, which means that the area under the curve is related to this graph. Specifically, this 150 miles is the exact change in the y value from the point at 10 minutes to the point at 20 minutes. And you can see those calculations work out right here. This seems obvious when we're just talking about distance and time, but it's actually totally unobvious. A theorem in calculus or in math is the equivalent of like a law in chemistry or physics. It's something that has to be true, that's been discovered and proven. And the first part of the fundamental theorem of calculus says that not just for this plane, but for any continuous function, little f, and any of its millions of antiderivatives, big F, this equation has to be true. The integral from a to b, which represents the area under the curve, has to equal the difference in the y values of this other function. That's actually a pretty powerful result. Not only is it a really useful function just for evaluating these math problems, but it's also trying to quantify in an equation this relationship between these two different functions. So before we get to the second part of the fundamental theorem, let's talk more about definite integrals. Here we've got another airplane. This airplane, instead of traveling at a constant speed, now has a velocity that's increasing, and that's because it's taking off. You basically know how to read this graph, and so consider these definite integrals. I've got 4 of them. Notice that the function in all of them is the same. Tell me what else you notice about these 4 integrals. Great, so hopefully you notice that they all start at 0, and the only thing that's different about the integral is the upper limit of integration. So if this integral is related to this situation here, what does it mean for me to say the integral from 0 to 5 of 15x dx equals 187.5? Right, what that means is that the area under this curve, up until 5, is 187.5. In this situation, we just discussed how the area under the curve really means the total distance. So that means 5 minutes in, that's how far the plane's gone. How about this definite integral? What does this definite integral mean? Yeah, this is saying in the first 10 minutes, it's gone 750 miles. And then what about these two? Exactly, this one's saying in the first 15 minutes, the plane travels 1687, and in the first 20 minutes it travels 3,000. So those statements actually seem really simple. They don't sound like the kind of statements that need calculus. In fact, they are very simple, and they are pointing out that we can treat these integrals not just as one-time problems, but as a pattern or a relationship between the x value at the top of the integral and the area. In other words, everything else is staying the same, so we can think of these kind of like functions. In fact, let's write a function table. As you know in math, a function table is often a useful way to try and quantify a pattern or a relationship that you notice. In this case, we want to talk about the relationship between the b value, the upper limit, and the value of the integral, the answer that we get at the end. Now, b value and value of the integral are pretty mathy ways to think about what was supposed to be a real example about a plane. So think about what the b value means. The b value is the end of the interval of time, and the answer is the total distance traveled. So instead of just saying a function table with the b value and the value of the integral, I could also think of this as a function table where I'm going to record time and distance. So now if I take these values from the integrals, the first one being 5 minutes, I can go ahead and record each of the upper limits and the values. And we'd end up with a table that looks like this. Now, this table should look kind of familiar. What function is this? What are its inputs and outputs? Right, this is actually just a distance function, which is kind of interesting because in this example, I'm not given a second function like I was in that first example. Here I have a velocity function, but somehow using only the equation for velocity, I've ended up with data points that represent a distance function. In fact, we can take this one step further. Even without thinking about antiderivatives, we could think about what would it mean to create an equation or a set of instructions that would instruct somebody to take a time value that's not necessarily on this chart and figure out what the value of the distance would be. If you think about what we did to use these inputs in order to get these outputs, this is what a function might look like. We'd probably call it d of t, d standing for distance, which is my output, t standing for the time. And then we want to write down a set of instructions for how to get this number. Well, how did we get this number? This number came from taking the integral from 0 to 5. Now, of course, 5 is the t value, so I would take the integral from 0 to t of 15x dx. Notice the variable change. I'll talk about that in a second. And when we evaluated this integral for 5 in the position of t and 10 in the position of t and 15 in the position of t, we got these outputs. So here's what's interesting. We've been used to, up to this point, thinking about integrals just as a number. Like the integral has an answer, which is a number, and a one-time thing. But looking at this pattern, we actually realize that integrals can also be used to define functions. What's most important that you take away from this is when you use an integral to define a function, the input value of the function is going to be a variable at the top of the integral. It is not the x inside. In fact, the x's inside have nothing to do with this function. Those x's, those belong to this other function, which is not the same thing as the function we're looking at. So this is the variable, the independent variable. X is just another symbol used as part of the integral. Let's talk more about this function. It's a function defined using an integral symbol. Well, that function, that's the second part of the fundamental theorem of calculus. I'm going to read this. It's a little mathy, but I'll ask you some questions and I think you'll piece it together. So a theorem, remember, is a rule that has to be true. So this is in sentence form a statement that has to be true. If little f is a continuous function, at least between a and b, then the function big F, which is a different function, which is defined by the rule integral from a to x of little f of t dt. In other words, this is a function defined kind of like this function, where the instructions are to plug in your input into the top of the integral. That's how this is defined. The theorem is saying that this is a function that has a derivative, so it's a real function. You can always find the answer. And this real function has a derivative at any x value that's in that range that you started with. And here's the big money right here, the derivative of this weird function that's defined using an integral, if we take the derivative of it, the derivative is f of x, little f of x. Now here's what's weird. The x in your answer is that variable that was the input of your original function that originally was part of the integral, not inside the f term. And this t and dt, those variables disappear. We'll talk some more about that in class. The big idea here is that you can define a new function using an integral, and that new function's derivative is exactly the same function that's inside the integral. Whoa. Okay, you're probably horribly confused, and you're going to be so happy when we do the examples, because they're so easy. We'll come back to the big idea, so don't give up on the big idea. But let's just take a look at some functions that are defined this way. On the screen, you see 4 functions. Each of these functions is defined using an integral. Your job is to explain what each of these functions means. In other words, what's its input, what's its output, and then find the derivative of each of these functions. I'll do the first one with you. So here's our function. First thing I need to know is, what is the input? As always, the input is x. And now we need to know what the output represents. So the output, of course, is y. But what does the value of y mean? It's the area under the curve of e to the sine t between 3 and x. And you can see that it depends, the area depends on x, because I have to know what the x value is before I can know what the area is. That makes it a function. Great. Now that you understand what this function is saying, let's find its derivative. By the fundamental theorem of calculus, dy dx, which just means take the derivative of this integral function, has to equal simply e to the sine of x. Now, practically speaking, what did I do? Yeah, I just took that function inside and I replaced the variable to become an x. 3 didn't affect my answer at all. I strongly urge you to think about the fundamental theorem of calculus in terms of the idea. Do not just get in the habit of automatically replacing the inside. You'll end up in problems later. The idea here is that that variable x becomes a function, and the t's do go away. Try this same process for 1, 2, and 3. Remember, explain what the function means, and then find its derivative, and make sure that you label the reasoning, which is by the fundamental theorem of calculus. So hopefully 1 and 2 were totally easy. Couple things to notice. Notice the substitution of the variable and that the dt goes away. Again, we'll talk a little bit about that in class. 3 I had to add in just to make it a little interesting, and maybe you were surprised when you saw the answer. There was a negative that was slightly unexpected. Notice what's different about 3. In 3, the x is on the bottom. The way that we set up this function, we think about x as being the b value. Remember when we did our table of values? The b value is the second number in the interval of time. Like if you're measuring from 0 to 5 minutes, b, 5 minutes, is the second number. You can't really measure from 5 minutes to 0, but if you did, you could imagine it being the opposite of measuring from 0 to 5, which is why we can't necessarily just substitute the variable x in if x is in the bottom. We need the x variable to be the top limit of integration in order to use the fundamental theorem of calculus. So in order to do that, I switched these to the order of them. But when I switch the order, I know that that turns my answer negative, so I have to add another negative out front to counteract that switch. After I do that, I now use the fundamental theorem of calculus, and there's just a negative coefficient in front. Let's take a look at one last type of problem. And since I'm out of time in this video, I'm going to do these last examples in another video. It'll be very short, but it's really important that you don't neglect to watch the second one. Thanks for sticking with it.